Hello, welcome to another video of communication system. So, in this video, I will discuss how to compute the spectrum of FM signal. Okay, so why we need to calculate the spectrum of FM signal? It's basically we need to find out the overall transmission bandwidth of the FM signal, right? And as far as our discussion in amplitude modulation, we know that spectrum of a amplitude modulated signal is essentially the translated message spectrum, and the transmission bandwidth is never exceeds the twice the message bandwidth. And we know that for double sideband suppressed carrier amplitude modulated scheme, the spectrum transmission bandwidth is the maximum, that is twice of FM, twice of the message bandwidth, right? But in case of angle modulation system, we know that the spectral components of the modulated waveform are not related in any simple fashion to the message spectrum. So the spectrum calculation or spectrum representation is not very straightforward, and we will see that the bandwidth of the angle modulated signal is usually much greater than the twice the message bandwidth. Okay. Okay. So now how to calculate the spectrum of FM signal? Let's see. So FM, we know that how to find out the time domain expression of the FM signal when the modulating signal is sinusoidal in nature, just like this, that mt equal to am cos of twice by fmt. Unmodulated carrier signal is given by ct equal to ac cos of twice by fct, and then we can find out the FM signal st as equal to ac cos twice by fct plus beta sine twice by fmt, right, where beta is the modulation index which is given, which can be expressed as kf kf am by fm, right? And we know that this kf is called the frequency deviation constant expressed in radian per second, and which is the frequency deviation constant of the FM system, right? So we know this thing, we discussed these things already. Okay, now 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 we will proceed from this expression, time domain expression, and we will see how we can calculate the spectrum of FM signal, right? Now st equal to this expression, cosine sidereal signal expression, right? So this is the FM signal expression, right? Now obviously we can write this as a in analytical form, that it is a real part of this exponential function, right? Obviously you can write this way, and again we can I can expand this and split this as this way, that is real part of ac e to the power j beta sine twice by fmt into e to the power j twice by fct. And we know that whenever we write a signal in terms of real part of some signal times the e to the power j twice by fct, this becomes the complex baseband equivalent signal. Okay, so we know that when we have a passband signal xpt, xpt, then the real part of xpt, which is a complex baseband equivalent signal, times the e to the power j twice by fct. So this is basically your complex baseband or complex envelope of the signal xpt. So similarly, using the same analogy, we can see that here in the expression of FM signal, this AC e to the power j beta sine twice by fmt, this is basically your basically we can consider this as a as as the equivalent complex baseband signal of the FM signal ST. Okay, so using the same analogy, so we have discussed this thing very in the early classes, right? So so this is the equivalent complex baseband signal of FM signal ST. So this is a passband signal. We can so out of this passband signal, this is your complex equivalent complex baseband signal of FM signal, right? And right. So then let's see. So how we can proceed. Now we have two parts in your expression of FM signal right now, right? One part is that it can be expressed as a real of this is the analytical form, right? This is the it is in general analytical form. So it is ST equal to real part of SBT into e to the power j twice by FCT, where SBT is the equivalent complex baseband signal of the FM signal ST, right? So your SBT, so now we have to find out the spectrum of S of t, a spectrum of this FM signal ST. So how we can find out the spectrum of this FM signal? So simply we can find out the FM signal. First I have to find out the spectrum of this SBT signal, this baseband signal, complex baseband signal. I have to compute that part, and then this ST is a passband signal. So the passband spectrum of this ST is nothing but the simply a frequency translation, is a frequency translation of the baseband spectrum. Okay, because it is multiplied by this e to the power j twice by FCT, right? Now now let's see how we can find out the spectrum of this complex baseband signal. Okay, so here probably you can see, so we can write this SBT as a Fourier series. Okay, so we can expand this SBT as a Fourier series. Okay, so this is the discrete Fourier series. So it is a complex Fourier series expression. So it is summation over minus n equal to minus infinity to past infinity Cn e to the power j twice by n FMT, where FM is the fundamental frequency. So you can easily see that this SBT signal is basically is a periodic waveform. So this is a periodic signal with period t equal to 1 by FM. Okay, t equal to 1 by FM. This is the period of this signal SBT. So how you can easily check that by this thing, that SBT should be equal to SBT plus K of capital T. So you can check that for any K, this is satisfying. So where t equal to 1 by FM, where t equal to 1 by FM. So this is the time period of this signal. So you can see that this equation is satisfying for any values of K when t capital T equal to 1 by FM. So that's why this is the so SBT is a periodic function with period t capital T equal to 1 by FM. Okay, now obviously we can expand SBT as a Fourier series then, and this Cn is the your coefficient of this for exponential Fourier series. So with a little bit of mathematics we can find out the value of this Cn easily, right, using the discrete Fourier series equation, or right, and with little bit of mathematics we can end up getting the expression of Cn as like this. Okay, so and we can see that this would be like this. Means you can find out Cn as a as this expression that Cn equal to AC is Cn equal to AC into 1 by twice by 0 to integration over 0 to 2 pi e to the power j beta sin x minus nx dx. Now what is this thing? So this thing is called the Bessel function of first kind of order n. Okay, so this is a standard form. So every Cn or the all the discrete Fourier coefficients, okay, which can be given by is simply equal to AC into Jn of beta, where this Jn is the Bessel function of first kind of order n. Okay, now so Cn is the nth coefficient. Now so nth coefficient of this discrete Fourier series, okay, of this. So and what is the discrete Fourier series of SVT, right? Discrete Fourier series of SVT, and which is given by this equation. Okay, so this is given by this equation, and we can compute the value of Cn by the properties of Fourier series, and we have seen that this is given by Cn is can be computed or as AC into Jn beta, where so this is the nth coefficient of this discrete Fourier series of this complex baseband signal of the passband signal SVT, right? And obviously then we can replace this SVT, so we can expand SVT as a complex exponential Fourier series by this formula, and we can replace the value of Cn by AC Jn, so AC into Jn beta e to the power j twice by n Fm t. So this is the equation for SBT. Okay, so this is BT, and so this baseband complex baseband signal. So this is the is a infinite Fourier series, right? Where you can we just replace the expression for this Cn by this Bessel coefficients, right? Now this is, and now we have to calculate the spectrum. Now we have calculated the spectrum of so we can we have understood that how to compute the spectrum of this SBT. Now we have to actually calculate the spectrum of this ST. So that is a passband signal, and that is given by real of this real part of this SBT into e to the power j twice by FCT. So basically we need to find out the Fourier transform of this, or Fourier transform of this signal, right? Now what we have to do? So this is very straightforward. Now what we have to do? Basically we have to ST will be real part of this SBT. I am just replace the value by discrete time Fourier series into e to the power j twice by FCT, and then little bit of again mathematics you can find out. So you can expand it in by using Euler's identity, and then you can just we can find out ST as a summation over minus infinity to infinity AC into Jn beta into cos twice by Fc plus nFm into t, right? So this way you can find out the spectrum, you can find out the time domain expression, which is very much convenient for computing the spectrum. Now you can find the spectrum easily, right? Now it is now using this discrete Fourier series, you can see that ST is coming into the form which is very much easy to find out the spectrum of the signal, right? Now simply we know that for a cos signal or a cosine waveform, continuous waveform, what is the Fourier series? So using the same analogy of this thing, we can find out the spectrum of this SR. So this is basically, So this is the Fourier transform of the passband FM signal. You can see that this is simply a there are infinite number of impulses in the in the spectrum. Okay, infinite number of sidebands, right? Okay, so analytically, so and where the amplitude of the sidebands is, you can compute by the AC into J n beta. So it depends on the Bessel coefficient of first kind. So this is the Fourier transform of the passband FM signal. Now we can understand the theoretical bandwidth will be infinite. So theoretical bandwidth of FM signal, basically it will be infinite, but practically the bandwidth will depend on the sideband with significant amplitude. And how we can determine that? We can determine that by analyzing this Bessel function. Okay, so we'll see that in another video, that how we can find out the practically so significant bandwidth which we should consider for finding out the transmission bandwidth of the FM signal. So theoretically the FM is having an infinite number of sidebands, so its total number of total number of sidebands is actually infinite, so its transmission bandwidth theoretically is infinite. But obviously we can find out a significant amount of bandwidth which we must consider when we are basically designing any FM system. Okay, and that would be determined by analyzing this the amplitude of the sideband amplitude, and which is determined by this Bessel function, right? Now so this is the basic idea behind how we can calculate the spectrum of FM signal. So what is the takeaway points from this video is that theoretically the bandwidth of FM signal is infinite, and practically the bandwidth depends on the frequency span of the sidebands with significant amplitude. We will see that how we can calculate the significant or practically usable bandwidth. Okay, so we'll see that in another lecture. Okay, but theoretically the bandwidth of FM signal can be considered as infinite. Okay, but okay, thank you. So if you have any question, please let me know.